Hi children, welcome to the new video of chapter 2, 1.3, revisiting irrational numbers. So we know in real numbers there are rational numbers and irrational numbers. Rational numbers are the numbers which can be write in the form of p by q, where p and the q are integers and q not equal to 0, while irrational numbers are the numbers which cannot be written in p by q form. We will prove that the numbers root 2, root 3, root 5 are irrationals, or in general we prove that root p, where p is a prime, is an irrational number. We know other some irrational numbers pi, root 2 by root 3, and non-terminating decimals like 0.10101, etc. Here is a theorem 1.2. Let p be a prime number if p divides a square, then p divides a, where a is a positive integer. So given that p is a prime number, and if p divides a square, then we have to prove that p also divides a. So given p divides a square, where a is a positive integer, that is a is an integer and it is also a positive number, let a is equal to p1, p2, p3, etc. pn. Here the p1, p2, p3, etc. pn are the prime factors of a. There is given a condition that these factors could not be distinct, like 16 have 2 into 2 into 2. The factors are 2 only, they are not distinct. Now a square equal to, we know a is p1, p2, p3, etc. pn. So x square is equal to p1, p2, p3, etc. pn into p1, p2, p3, etc. pn. X square can be written as p1 square, p2 square, etc. pn square. Given p divides a square, that is p is a prime factor of a square, that which implies that is p is one of p1, p2, etc. pn is p, but a is equal to p1, p2, etc. pn. That implies a is equal to, let p take outside, p into p1, p2, etc. pn. That is p is a prime factor of a, p divides a. So we get, if p divides a square, then p divides a. Next theorem 1.3, root 2 is irrational. That is, we have to prove that root 2 is rational. For that, assume that the root 2 is rational, so it can be written as p by q form. Let it be r by s, where s not equal to 0. If r and s have common factors other than 1, then like 6 by 4, we can write it as 2 into 3 and 2 into 2. 2 is common factor in numerator and denominator, so it can be cancelled. So we get a fraction with the coprimes 3 by 2. Like this, we can assume that root 2 can be written as a fraction of coprimes. Let a and b are coprimes, so that root 2 is equal to a by b. Squaring both sides, we get root 2 square equal to a square by b square. Since root 2 square is 2, we get 2 is equal to a square by b square. Then taking b square into other side, we get 2 into b square is equal to a square. That implies 2 is a factor of a square. That is 2 divides a square. 2 divides a square implies 2 divides a, that we have done before. If P divides A square, then P is also divides A. Since A is prime, 2 cannot divide A. This is a contradiction to our assumption that A and B are coprimes. This contradiction we got by our assumption root 2 is rational. So we can conclude that root 2 is irrational. Next we have a problem, prove that root 3 is irrational. For that we assume the contrary, that root 3 is rational. Then it can be written in the form of a by b, where b not equal to 0 and a and b are coprimes. Squaring both sides, we get 3 is equal to a square by b square, and we can take b square to other side, then we get 3 into b square, that's equal to a square, which implies 3 divides a square. By theorem 1.2, we can say that 3 divides A. 3 divides A means A can be written as a multiple of 3, like 3 into C, where C is an integer. So, but we have already proved that 3 into b square equal to a square. In a square, we can substitute the value of a is equal to 3c. We got 3b square equal to 3c square. That is 3b square equal to 9c square. B squared equal to 3c square, which implies b square is divisible by 3, that is 3 divides b square, that implies 3 divides b. So we got 3 divides a, also 3 divides b. Since a and b are coprimes, 3 cannot divide both a and b, so our assumption root 3 is irrational is not true. Therefore, root 3 is irrational. Next question. Show that 5 minus root 3 is irrational. Let assume 5 minus root 3 is rational. So, by the property of rational numbers, we can say that 5 minus root 3 can be written as a by b, where a and b are coprimes and b not equal to 0. Now changing the position of root 3 and a by b, we got 5 minus a by b is equal to root 3, that is 5b minus a by b is equal to root 3. From this we can see that root 3 can be written in a p by q form, where p and b are integers. So this contradicts the fact that root 3 is irrational. So we have already proved that root 3 is irrational, which cannot be written in the form of p by q, where q not equal to 0 for some integers. We assume wrongly that 5 minus root 3 is rational. Therefore, we got 5 minus root 3 is irrational. Next question, example 7. Show that 3 root 2 is irrational. Assume the contrary, that 3 root 2 is rational. So let A and B are coprimes, and 3 root 2 can be written as A by B, where A and B are coprimes and B not equal to 0. Taking 3 on to the other side, we get root 2 is equal to a by 3b. So here we have seen that root 2 can be written in a p by q form, where p and q are integers, which implies root 2 is rational, which is a contradiction that we have already proved that root 2 is irrational. Therefore, our assumption 3 root 2 is rational is wrong. Therefore, we can say that 3 root 2 is irrational.